Hey guys, welcome back. So last time we were looking at two separate problems. The first one, job scheduling, and the second one, which I've erased, was load balancing. And they seem like similar problems. I mean, they both involve like jobs. We're trying to schedule a maximum set of jobs over here. With the load balancing one, we're trying to schedule all the jobs such that no single machine, was out of whack where it had a huge load on it while other ones had small loads on it. Okay. Well, the bottom line was they both seem like they could be difficult problems, but as it turns out, the load balancing is a very difficult problem, but job scheduling itself turns out to be a very easy problem. And just as a quick review, job scheduling, we have n jobs. Each job's going to have a start and a finish time, and we want to find a maximal subset of those jobs such that no two jobs in that subset conflict with each other. And like before, we usually have it represented like a picture like this. So for instance, job 1 would be conflicting with job 2 here. And what might be a maximal subset? Well, what can we do? Well, look here, we can include job 1, 3, 4, and 7. That's probably the best we're going to be able to do. Okay. Well, what I told you last time is job scheduling is easy because there exists an optimal greedy algorithm to solve it. Okay. Well, you can take my word for it, or you can wait a couple lectures where I prove to you that there in fact is an optimal greedy algorithm. But before we figure out, which greedy algorithm is optimal and prove it's optimal, we have to, at least come up with some candidate greedy algorithms which may or may not solve this problem. And we talked about one last time, or I mentioned one last time, and that was, I'll write out greedy algorithms here. Greedy algorithms. And the greedy algorithm we talked about last time was shortest job first. Okay, so maybe that's number 1 here. Shortest job first. And just to explain that algorithm, in plain English, colloquially, it would be, okay, we order the jobs based off their size, then we include the first job, and then we check the next one. Does it conflict with our current set? If it doesn't conflict, then we add that job in. If it does conflict, we move on to the next one, and we keep doing that, building our schedule until we've checked every single job. So we'll get to figuring out if this is an optimal greedy algorithm or a suboptimal greedy algorithm. But before we do that, we're in the brainstorming phase of determining which greedy algorithm we may use, which greedy algorithm we may not use. So the goal here is to kind of just, maybe come up with between 5 and 10 potential greedy algorithms. And then, there might be some that are clearly suboptimal, maybe some that could be optimal, and we'll take it from here. But we're in the brainstorming phase. No bad ideas in brainstorming. So let me give you one more greedy algorithm we could do, or may be a good idea, probably isn't. But we have shortest job first. Why not do largest job first? Is that a greedy algorithm? Largest job first? Well, yeah. What is a greedy algorithm? Well, remember, we don't care about the big picture. We just want to look one step ahead, one choice at a time, and we make that choice based off, a single rule, a single heuristic, a single criterion. And up here, we're doing it based off size, and we're looking for the smallest job. Here, we still have a greedy rule. We're again using size, but we're going to do it with the largest job. So, if we weren't plagued by the coronavirus right now, and I had, a good solid 100 of you in front of me, what I would do is, leave it as an exercise. You guys talk amongst yourselves, come up with, a few more greedy algorithms when we talk about it. As such, I can't really ask you to do that because you're not here, obviously. So I'm going to basically just have to give these greedy algorithms to you right now. But if you want to come up with a few, there's a few, I'd say, easier to come up with, maybe a couple, or at least one that's less easy, less intuitive to come up with. But if you want to try to come up with some, pause the video right now because I'm about to basically just blast off a few here. 1, 2, 3. Okay, that was your chance. Well, jobs have a size, but we also have some other parameters about jobs we could use. We have a start and finish time. So why don't we, base our greedy rule based off the start time or the finish time? What do I mean by that? Well, maybe I'll do earliest start time. Earliest start time. So over here, I'd say, well, what's the job with the earliest start time? Well, that's job 1. I decide to include that. What's the next one? That's job 3. Or sorry, let's backstep just a little bit. What's the next one? That's job 2. Does it conflict with my current schedule, which has job 1 in it? Yes, it does. So don't include that one. Then go to the next earliest start time, job 3. Does that conflict with my current schedule? No, so add that, and so on and so forth till I've exhausted all the jobs. So that's earliest start time. Okay, sure. And similar to what we did with the job size rule, well, if we have earliest start time, why not do latest start time? Why not? It's brainstorming. No bad ideas in brainstorming. Latest start time. And I'll call this EST, LST. You can figure out how I came up with those names. 5, well, we used the start time, right? And job size. Well, what else we have? Of course, we have the finish time, right? So why not do, and I'm not going to write this out, but earliest finish time and latest finish time. Latest finish time. So I would say, you know, about here, these are the ones that I would hope that you'd be able to come up with, right? These are the most intuitive ones. We have job size, we have a start time, we have a finish time. It's, you know, relatively easy to come up with a greedy algorithm that says, okay, just order them based off that parameter and go through based off that rule. Are there any other potential greedy algorithms that we could come up with? Well, I'm sure, you know, there's some kind of theorist out there that would tell me, oh, Professor Macchio, there's actually an infinite number. Yeah, I get you. But let's see if we can come up with some other intuitive ones. Well, what are we trying to do? Find a maximal subset, and I didn't write it out, but which doesn't conflict, right? We want to find a set of jobs which don't conflict with each other. Well, what if I were to look at a schedule and say, okay, find the job that has the least number of conflicts? That seems like a pretty good idea. I mean, that's what we're really trying to do. We're trying to find a maximal subset of jobs that don't conflict with each other. So that makes sense. Let's look at the jobs, order the jobs based off, you know, least conflicts. And you probably already see where I'm going with this. Flip that sucker. Most conflicts. Remember, there's no such thing as a bad idea in brainstorming. Okay, so I'm content with this for now. 8 greedy algorithms, 8 greedy candidates here. And I want to figure out, of these 8, is there an optimal greedy algorithm? Is there, you know, more than one optimal greedy algorithm? Which ones are suboptimal? And that's really the question. So how would you figure out, or, you know, maybe not prove right off the bat, but let's say you want to gauge, get an idea for which ones are optimal potentially and which ones are suboptimal. Well, remember, it's relatively easy to prove a greedy algorithm is suboptimal. What do we have to do to prove something is suboptimal? Well, all you have to do is come up with a counterexample. And let me give you an example. I'm going to prove to you that shortest job first is a suboptimal greedy algorithm, or if you prefer, is an incorrect greedy algorithm. So to come up with a counterexample, I'm just going to draw a picture, and let's say I have job 1, job 2, and another job here. And hopefully you can gauge the scale here, but this is job 3 in the middle. It doesn't matter if you can see the 3 or not. But I have this one big job, this other big job, and this small job, which conflicts with both of these big jobs here. Well, hold on. What would shortest job first do? It says, okay, this small job here, it's the shortest job, put that in the schedule. And then you continue on, maybe this is the next shortest one. Does this one conflict with my current schedule? Yes. So don't include it. Does this other one conflict with my current schedule? Yes. Don't include it. And it would return to you the schedule with just the job number 3 in it, just one job. Is that optimal? No, that's a suboptimal solution. Why is it suboptimal? Well, clearly the optimal solution is to take the 2 large jobs. Okay, so shortest job first is suboptimal. What about largest job first? Is that one suboptimal? Yeah, of course it is. Come on. It would have to, the foundations of logic seems like it'd have to fall apart for that to be optimal. And my marker's running out. Hopefully we can make it to the end of the video. But a counterexample for largest job first being suboptimal is just something like this. Maybe I have 1 billion small jobs there. It doesn't really matter, right? Get the point across. I just need 2, really. But what's going to happen here, it takes this large job and all the other small jobs that should be included in the optimal schedule are now excluded, and it returns a suboptimal solution. Okay, what about some of the other ones? Well, take a moment and take a crack at it. And while you're doing it, if you try one example and maybe you do something like, I don't know, earliest start time, right? You do one example and you see, oh, earliest start time actually returned the optimal solution here, an optimal schedule. Does that mean that it's not suboptimal? Meaning, does that mean that it's optimal? No, of course not. Just because, it returns an optimal solution for one example doesn't mean it's an optimal algorithm, right? So you have to kind of try a few examples, try to figure out exactly what it's doing, and maybe, cleverly construct a counterexample where it exploits some weaknesses of that algorithm, exploits some certain behaviors. And I'll tell you right now, at least one of these algorithms, and we already showed that these are suboptimal, so at least one of these remaining algorithms is optimal, at least one, potentially more than one. Well, how do I find that? Well, again, it's a little harder to prove something's optimal, but what I would like for you guys to do is, take a moment, try to figure out some counterexamples to this. Maybe for a few of them you can't come up with a counterexample. And then that at least narrows it down to say, oh, maybe these 3 algorithms here I can't find a counterexample to, therefore now I'm going to move ahead and try to prove that they're optimal. Right? And that's kind of an organic way to solve this problem. So pause the video, check it out. 3, 2, 1, pause, and I'm back. Okay. Well. Which ones were you able to come up with counterexamples for? Earliest start time. Okay. Well, actually I already have a counterexample on the board for earliest start time. What's that? This one. It's the same as the longest job. The earliest start time is going to be this big job here. This particular greedy algorithm is going to grab it. And of course, we already know that that's a suboptimal example. Latest start time. You know what? Latest start time, I think it actually works for these 2, right? So latest start time is going to be this one, then it's going to grab this one, then this one, this one. So latest start time actually returns an optimal solution for that example, and it grabs 2 and then 1 here. So you know what? That doesn't prove that it's optimal, but at least these typical counterexamples, they don't prove it suboptimal. Maybe I'll leave that one for now. Earliest finish time. So if I do earliest finish time, for instance here, which one finishes first? This one, then grabs this one, then this one, then this one. So kind of similar to latest start time, it returns optimal solutions. And here's one thing that maybe some of you observed. Let's think about, a picture like this for a moment. What if we were to hold a mirror here and take like a reflected image of it? Well, if I were to take a reflected image of this picture, all the conflicts between the jobs remains the same, right? If I just take a reflection of it, 3 is still gonna conflict with 2, and 4 is still gonna conflict with 5 and 6, and so on and so on. But what changes? Well, really the only thing that changes is the earliest finish time becomes the latest start time, and the earliest start time becomes the latest finish time. So there's actually a strong coupling between latest start time and earliest finish time, as well as earliest start time and latest finish time. Now that's not a formal proof, it's just kind of like a hand-wavy argument. I mean, you can formalize it if you want, but it shouldn't be too hard to convince yourself that that's the case. It's almost like you're just reversing time. Remember, time is on this x-axis here, and it's kind of implied that this is 0 and we extend to infinity, but nothing really says that, 0 couldn't be over here and infinity extends that way. So it's just reversing time. It's the same picture, same conflicts. We just have a different notion, a mirrored notion of earliest and latest. So what does that mean? Well, again, this isn't a formal argument, isn't a formal proof, but if this algorithm, earliest start time, is suboptimal, that's going to be true if and only if latest finish time is suboptimal, which also implies that if earliest start time is optimal, that's true if and only if latest finish time is optimal. So we could come up with a counterexample for latest finish time. However, based off the reasoning I just said, because we know earliest start time is suboptimal, we know latest finish time is optimal. Okay, let's look at most conflicts. Most conflicts. Do we have a counterexample to most conflicts on the board right now? Yeah, we do. Is it this one? Well, oh, actually it is this one. It's both of them. I was thinking it was going to be this one, but of course this one's also a counterexample. So for instance, most conflicts, we're going to grab this big job because it conflicts with 4 other jobs. All these other small jobs just conflict with 1. So we're going to grab this one, back ourselves into a corner. Over here, we're going to pick this job in the middle because it conflicts with 2 jobs, and each of the larger jobs just conflict with 1. Both of those lead to suboptimal solutions. So what do we know so far? Well, shortest job first is suboptimal. So is largest job first. So is earliest start time, and therefore so is latest finish time. Most conflicts is also suboptimal. Well, that leaves 3 potential candidates here. Least conflicts, earliest finish time, and latest start time. So, were you able to come up with counterexamples for any of those? I'll say this right now. At least one of these algorithms is suboptimal. So I would say of these 3 algorithms, if it is suboptimal, if any of those are suboptimal, it's pretty hard to come up with a counterexample for them. And again, if you were here, we'd kind of discuss it, but I just kind of have to give it away unless you want to pause it and play around with a few more things. I'll give you an opportunity right now. Freeze frame, unpause, okay? Here's the deal. Least conflicts is actually suboptimal. Well, if you weren't able to come up with a counterexample for least conflicts, you're certainly forgiven. It's actually one of those ones where it's very difficult. You have to be very clever to come up with a counterexample for least conflicts. And I'm kind of racking my brain right now being like, gee, I hope I remember what that counterexample looks like, because I'm what? I don't know, maybe 15 minutes in and I don't want to, pause it, look at my notes. That'd be weak, right? So let's see if we can come up with it. Okay. I'm going to draw 4 jobs in a row. And this is me trying to construct a counterexample for most conflicts. And the idea is I'm going to have these 4 jobs be the optimal solution to this particular job scheduling problem. And let's see what I do here. I'm going to try to construct my example. So I choose a job that has the least number of conflicts that, after I make that choice, I back myself into a corner, kind of shoot myself in the foot, and I can't choose these 4 jobs. How am I going to do that? Well, check this out. Yeah, this will work. So look at that schedule. Which job has the least number of conflicts? Well, we can go through how many jobs does this one conflict with? 3. How many jobs does this one conflict with? 4. This one conflicts with 3. And we can write these in, why not? 3, 4, 4, 4, 3. Here's the, and again, you don't really need to see these numbers. I know it's probably too small, but here's the bottom line. How many jobs does this job conflict with? Yes, that's right. I heard it in the back. 2. Well, hold on, and you know, this is gonna be, well, hold on, this one's actually 4. Doesn't matter. 4, 4, 3, 4, 4, 4. So what happens here? Well, lease conflicts, I'm gonna choose this job. That's gonna be the first one I choose to start off my schedule. What happens? That's right. I can no longer choose these 2 jobs. But what do I know? The optimal solution is exactly, precisely those 4 jobs. So as soon as I choose this job, dead in the water. I'm done. If I choose this job, it's going to be a suboptimal solution. Every subset of jobs that includes this job in it is a suboptimal solution. And that's the first one I choose when I'm using lease conflicts for this particular one. Therefore, that's a counterexample, and lease conflicts is suboptimal. I will say, maybe you kind of discovered this through the exercise of it, that it's pretty good. I mean, lease conflicts usually does find an optimal solution, but that's not good enough. Remember, it's not good enough to find an optimal solution most of the time. We need it all of the time for all problem instances. Okay, well, what does that leave us with? Well, we have these 2. And remember, I said if one's optimal, the other's optimal, and if one's suboptimal, the other's suboptimal. I'm telling you right now, these are optimal. And we're going to really zone in on earliest finish time. So we're able to prove all of these are suboptimal. Now we have to prove that earliest finish time is optimal. So I'll give you the pseudocode next time, and we'll prove that it's optimal next time in the next video. But I just want to get one thing across. You know, you could show example and, you know, a bunch of examples, 1 example, 2 example, 3 examples, a billion examples where earliest finish time returns optimal solutions. I don't care, right? That has no implication. That does not prove that it's going to be optimal for all problem instances, right? I could come up with an infinite number of problem instances where shortest job returns me an optimal solution. So you can't show me any number that earliest finish times returns an optimal solution to convince me that's an optimal algorithm. We actually have to prove that it is optimal for all problem instances. And we can't just do that by exhausting problem instances because there's an infinite number of problem instances. So how do we do that? Well, you'll see it next time. You know, we have to get a little bit clever with our math, basically a proof by induction, but that's for the next video. I'll see you guys in the next video. Thanks for your attention.